Okay, and last section for today is on implicit functions. So far, we've been expressing functions of one variable in terms, so functions, what did I write here? Functions have expressed one variable in terms of another, or several, like we just started today. So we had something like y is equal to f of x, which is equal to 1 minus x squared. So this is sort of the nicest way of presenting a function. It's like you give me a value of x, I know exactly how to tell you the corresponding value of y. So I have this, or I have something like y equals sine x divided by x. So I have y on the left side of the equation and only x's on the right side of the equation. So an implicit function is defined by a more general relationship between the variables. So I could say something, so this is the equation of a circle. So I say x squared plus y squared equals 1. And this is, if I'm on a circle of radius 1, this is going to be true for every point that's on that circle, and it's going to be false for every point that's not on that circle. And this one, if you think about what I've done up here, it at least has kind of an easy way to go between the old, or the specific definition of a function. So this is, in high school I had to do something called the vertical line test. So if I have a function and I find the intersection of that function with any vertical line, it can have at most one point where they cross. If it's like a circle and it crosses twice, then it's not a function. So for a given x, there has to be a unique value y. The circle's not going to have that property except for 2 points, one at either end. But it's not that bad either. It's very easy to fix. I can just chop it into a top circle and a bottom circle. This one we're going to see is not quite so well behaved. So in some cases, you can just solve for one function as another. In any one of these functions, any function that I can write f of x equals some expression of x, I could just move all of that to one side of the equal sign and say it's an implicit function. And the way we're actually going to define this is I'm going to say that f of x, y, z is a function of 3 variables, and the set of points that satisfy f of x, y, z. So I just chose x, y, and z. It could be just x and y, or it could be many, many more variables. This is just kind of an example with 3. So in this case, the implicit function is going to be the set of points that satisfy f of x, y, z equals 0. And in that case, I'm going to call that set of points where this condition holds the locus defined by f. So sort of like I mentioned before, if I have the equation of a circle, x squared plus y squared equals 1. If I'm on this circle, then this statement is going to be true. So any point on this circle of radius 1 is going to satisfy this equation exactly. If I'm inside the circle, x squared plus y squared is going to be less than 1. And if I'm outside the circle, it's going to be greater than 1. And I have this one set of points that satisfies this. And so that's going to be my locus. So it's got infinitely many points in it, because this is it's a line, it's continuous. For any 2 points on the circle, I can find a point in between them that's also on the circle. But in this case, I can fix it pretty easily. So I can say y equals 1 minus x, square root of 1 minus x squared. That gives me the blue curve, which is the top semicircle. And then I can say minus square root of 1 minus x squared, and that gives me the red curve, which is the bottom semicircle. This one, on the other hand, has a locus that looks like this. And so this is more difficult. Maybe there's some hope that on the left side of the y-axis, so over here, you can solve for, at least here it passes the vertical line test. So maybe you could solve this and get an expression y equals something. Well, not maybe, you can, but it's not very much fun. on the right side, until you get to this point over here where this little loop ends, it doesn't pass the vertical line test. So here, for instance, a vertical line would intersect the function 3 times. But we might still want to be able to take a derivative of either of these functions. So suppose I want to find the slope of a tangent line to the unit circle. So that circle I just had a picture of that has radius 1, that's called the unit circle, because the radius is 1 unit. So I have to split this up. If I want to do this using regular functions, I have to split this up into 2 cases. I have to consider the top semicircle and the bottom semicircle independently. But I can use the chain rule to sort of help me out here. So what I'm going to do is take the derivative. I have y equals the square root of 1 minus x squared. And I'll take the derivative of both sides of that equation with respect to x. And by the chain rule, when I'm taking the derivative of y with respect to x, I have to multiply. So I'm going to take the derivative of y, but that's just going to be 1. So there's kind of an invisible 1 over here that I didn't bother to write down, times the derivative of y with respect to x. And remember, this is what I'm trying to find. This is the derivative. And on the right-hand side, I'm now going to take the derivative with respect to x. And this should be pretty easy because it's just a function of x. So I'll rewrite the square root as quantity to the 1/2 power, so it's easier to use the power rule. And then cheat a little bit with the chain rule again. So here, the derivative of the inside of this quantity, derivative of 1 is 0 because it's a constant. The derivative of minus x squared is going to be minus 2x. So the chain rule pops that minus 2x out here. And if I simplify, so the 2 is going to cancel out the 1/2 that popped out here because of the power rule. So I end up with minus x divided by the square root of 1 minus x squared. And then case 2 is going to be very similar, except there's going to be a minus sign here. So I'll just skip down to the bottom. And we get exactly the same thing, except now I have the minus sign down here. And when I don't bother canceling out a minus sign, it's because I have something clever for you coming in the future. So just keep this bit in mind, that this is minus x divided by the square root of 1 minus x squared. And this is minus x divided by minus the square root of 1 minus x squared. And so now I'm going to try doing this using the idea of an implicit function. So if I take the derivative of a function of y squared, by the chain rule, I can take the derivative of this with respect to y and then multiply by dy dx. So this is the same thing I did on the previous slide, except now I have a y squared here instead of a y, so it doesn't just go away. So instead of having my invisible 1, I end up with the derivative of this, 2y, times dy dx. Let's see, what am I getting at here? Oh, okay. So this is my little result, and now I'm going to try and take the derivative of the equation of a circle, the implicit equation of a circle, with respect to x. So I still have the linearity property. So here I want to do the derivative of a sum. So that's just going to be the sum of the derivatives. And then on the right-hand side, I'm just going to take the derivative of 1. 1's a constant, so hopefully we get 0 over there. Oh, we do. And when I split this sum up into 2 terms, I end up with the derivative with respect to x of x squared. So that's going to be easy to do because I've got my function already in the right units, in the right variable. And then when I want to take the derivative of y squared with respect to x, that's when I'm going to have to use this result that I went through up here. So I'm going to just end up with 2y dy dx. So I end up with this expression here, 2x plus 2y times dy dx. But remember, I'm trying to find the derivative for this tangent line touching the circle. And dy dx is going to be the slope of that tangent line. So dy dx is what I'm trying to get. So I'm just going to solve for dy dx now. So I subtract 2x from both sides and then divide by 2y. So I end up with minus x over y. And now remember, when I did my two cases, I had to have the top half of the circle, that was y equals the square root of 1 minus x. And so when y is greater than 0, this is what I would get. And when y is less than 0, then I get the bottom half. But in both cases, oops, I guess I can't highlight just the denominator here. In both cases, the denominator is just the value of y appropriate for where I am on the circle. So if I don't insist on getting rid of y entirely, I can actually express both of these as this one formula, dy dx equals minus x divided by y. And so the only caveat, so the thing you have to be careful of, is that this is only going to hold for points in the locus. So, I can still evaluate this at the point 1, 1 and get negative 1, but that has no interpretation for what I've done because the point 1, 1 is not on the circle. Okay, and then just for fun, I did, so this funny shaped thing with the loop in it is called a folium, which I guess is Latin for leaf, and somebody thought that that little loop looked like a leaf. So here it's going to be a little bit trickier, but we're still going to use all of the properties exactly the way we had been doing it. So I'm just going to take the derivative of both sides of this equation with respect to x. Since here I have a product, so it's x times y, I'm going to have to, oh, whoops. Yeah, so I need to treat x and y, so I'm kind of imagining y is a function of x, even though I can't actually write it down that way. So what I did here, on the left-hand side, I just used linearity to write the sum as a derivative of a sum as the sum of the derivatives. And on the right-hand side, I had to use the product rule. So I used 6x times y. And so I get the derivative of the first function with respect to x is 6 times y. So that's where this came from. And then I'm also going to take the derivative of the second function, which is y. So I'm going to take derivative with respect to x of y times the first function, which is 6x. So that's where this second term comes from. It's just the product rule. But the derivative of y with respect to x, so that's what I'm looking for again. That's dy dx. So technically, it's the chain rule. So I take the derivative of y with respect to y times dy dx. But really, you can just think of this as going straight to dy dx. But now I've got this dy dx on both sides. But I'm just going to use algebra to move both of those terms to one side of the equation and everything else to the other side. So I'm going to end up with, so here I had a positive 3y squared. That's where this came from. And then I had a 6x on this side. But when I move it to the other side, it'll become minus 6x. So I have 3y squared minus 6x times dy dx. And then everything else, so 6y minus 3x squared on the right-hand side. And then I'm just going to divide both sides by 3y squared minus 6x. And that gives me an expression for my derivative. And again, so I think, okay, let's see. 2y minus 6, yeah, so you have to be a little bit careful with this again, because, again, it's only going to be defined when I'm on the curve. So if I take any other point, I'll still be able to evaluate this, and it will give me a number, but that number has no interpretation for what I've just done. This only gives me the derivative for points that are on this curve. And then there's still one small problem. So if you look at where the curves cross, I actually should have two derivatives somehow here. I have one flat derivative and one infinitely steep derivative. And so the way you're going to capture that is that's at the origin. So that's at x equals 0, y equals 0. And if x and y are equal 0, then this is 0 and this is 0. So I get one of these numbers that do not exist. And so in that case, you would just have to examine the function and try and figure out what its behavior is here. But since it's crossing the derivative, it's not going to be differentiable at that point. is that the whole idea doesn't really make any sense. So it's, I couldn't say, if I wanted to add h to this, would it be h going up this way or would it be h going out that way? I can't do that with just one h, so you'd have to do something more complicated if you wanted to extend the idea of a derivative to this one point where the curves cross.